Hello again. For this video, we'll cover the fundamental tool application, at least the beginning of that, for Chapter 5. That is, we're going to analyze a single investment alternative. We'll look at the cash flows for that investment alternative. And once we examine those cash flows, we'll determine whether or not it's an attractive investment. In this video, we'll look simply at two different tools that we'll use. The present worth, we'll look at present worth analysis. We'll look at future worth. And we're also going to slide in here the capital recovery factor. And we'll talk about that a little bit. So just to recap, when we're looking at an individual investment, the way we will analyze this is to take all of the cash flows for that investment, the initial investment, any periodic cash flows that occur over time until the very end, when we might dispose of this asset, whatever it might cost or whatever return we might gain from disposal of that asset. So cradle to grave kind of thing, all of those costs. And to apply the present worth analysis, we will find the present worth of all of those cash flows. The interest rate that we'll use to move those cash flows is the MAR. And if that present worth evaluated at the MAR is greater than 0, that's a good investment. And if the present worth evaluated at the MAR is less than 0, then we determine that that's not a good investment. It does not achieve the MAR as a rate of return. So if the present worth happens to be greater than 0, not only are we earning the return, the MAR, we're earning a little bit more, whatever that difference is between 0 and the net present worth. That's a present value of a return over and above the interest rate indicated by the minimum attractive rate of return. We also could analyze those according to the annual worth. Take all of the cash flows, analyze all those cash flows, look at the annual equivalent uniform amount, the A, for all those cash flows. If it's greater than 0, it's a good investment. If it's less than 0, it's a bad investment. Look at the future worth. Look at some time in the future. Perhaps it's at the last end of the last cash flow when we dispose of the asset. Look at the future worth at that time. Evaluate it at the MAR. Take all of the cash flows, investment, periodic payments, everything at the end. Find the future value, and if that's greater than 0, it's a good investment. Less than 0, bad investment. All of those tools will give you exactly the same result. That is, they won't give you the same number, but they will tell you, they will all say good investment or they will all say bad investment. So which one of those tools you might use might be dependent on the data that are given, might be whatever your organization's particular bent might be in solving those problems. So we'll look at a problem in that regard. We'll also examine the capital recovery factor. Let me talk about that very briefly. The capital recovery cost is a number that represents the equivalent uniform annual amount of simply these two elements of the problem: the initial investment and the final market value. Only those two. So you take the initial investment and you move it across time. You find an equivalent uniform annual amount, an A for the initial investment. You find an A for that market value at the end. When you dispose of the asset, you have an A. You spread that out as an A over time. You add those two numbers together. Whatever the sum of those is, it's an annual amount representing the initial investment and the final market value. That annual amount is called the capital recovery cost. Any periodic payments any periodic maintenance costs, operating costs, revenue, all of that is irrelevant. You need to keep that in your mind because I know there'll be a question on a quiz about this. All of that is completely irrelevant. The only thing that the capital recovery factor takes into account is for the capital investment that you made, the cash flows related to that. The initial investment in this asset or project and the final market value. So that's it. We're going to look at a couple of example problems pretty quickly. These problems are from questions in the back of chapter 5. So these might come in handy for all sorts of things. You never know when or where. But let's pull those in. We'll demonstrate the use of these tools, and then we'll save the other things that are covered in this part of the chapter of the bond problems. We're saving those till later, till we meet face to face. We need a good bit of interaction to get through the bond sorts of problems. So we'll save it for that. And on the next video, we'll look at a couple of more tools that help us analyze individual alternatives. So let's get directly to the problems we're going to examine today. This is problem 5.4 in your textbook, and I'm gonna, if you have it, you can be good for you to follow along. I'm gonna kind of read it briefly here, and I will input the cash flows that are related to this problem. The question asks us to evaluate a combined cycle power plant on the basis of the present worth method when the MAR is 12% per year. There's our MAR, 12% per year. Pertinent cost data are as follows, and it gives us the following data. The investment cost is $13,000, and the useful life is 15 years. So you can see that I built a cash flow table here that goes down to 15 years. At time 0, my initial investment is negative $13,000. The other piece of information that's relevant here is the market value at the end of year 15 is $3,000. So at the end of year 15, we can we're going to take this power plant, and the market value at the end is $3,000. By the way, these are in thousands of dollars, so that would be 3 million. But we're just going to keep it at the thousands level here, $3,000. The annual operating expenses are $1,000. So every year we incur an expense of $1,000. I'm going to copy that down until we get to year 15. You can see there may be a problem when we get to year 15 since we already have a number there. So in year 15, we have negative 1,000 plus 3,000. So I'm going to go ahead and drag that down, negative 1,000 plus 3,000. And if I put an equal sign in front of it, it may actually give us a number. And that's a positive $2,000. Not exactly sure why it's giving me red, but we're going to make it black and take away those extra decimal places. Okay, $2,000. Now there's some additional information here. There's an overhaul cost at the end of the 5th year. It's $200. At the end of the 5th year, there's an overhaul that will cost us $200. So I'm going to remember to put the equal sign here. Negative 1,000 minus $200, or negative $1,200. And there's also an overhaul cost at the end of the 10th year. And at the end of the 10th year, this cost is $550. So there's our new cost at the end of the 10th year. Okay, that's all of our cash flows. Notice that I've stuck to the convention that we need to pay attention to, and that is negative cash flows. Expenditures are represented by negative cash flows. And income, the only income we have in this problem is a positive value here, and that's the positive $3,000, and added to the negative 1,000 operating expenses. So how would we analyze a problem like this? Well, first of all, in the introduction to this video, I said that if the present worth evaluated at the MAR is greater than 0, then it's a good investment. If it's less than 0, then it's not a good investment. Well, I'm pretty sure that when we find the present worth of this investment, it will be negative, because there are no positive cash flows at all until 15 years down the road. And when we bring that small amount, that $3,000, back to time 0 from 15 years in the future, it's going to be really, really, really small. So this present worth will be negative. What does that mean? Well, in this problem, we're just applying the tools, so we really don't need to worry about that. But it does bring up the issue of cost alternatives, and that's exactly what this is. There are sometimes some alternatives that aren't really investment alternatives. This, we're not expecting to earn money, it's just something that has to be done. So for this problem, we're building a power plant, and we're trying to perhaps minimize, look at the cost, and want to minimize the cost of the power plant. And these are the data that we have in terms of cost. So what we'll do here for this problem is just find the present worth of those cash flows, and they will be negative, but we don't have to worry about the fact that it's not positive, because it's not an investment alternative. It's something that has to be done. So here we go. Well, how do we find the present worth? Well, we spoke previously about that NPV function, and I'm going to use it here. But let's see how we build this. First of all, remember we want the present worth. That's at time 0. Remember, the NPV function is going to give us the present worth 1 year before the first cash flows that are in our in the range that we provide as an argument. So if I want a time 0 present worth, then the time 0 cash flow I have to put in by itself. That's already at time 0. And our NPV function will begin at the end of year 1. The MAR was 12%. And then what are our cash flows? Our cash flows begin here at the end of year 1, and they'll go all the way through the end of year 15. And I'm going to close that function. And there we go. The net present worth of those all those cash flows is negative $19,500. So that's the number that we would use if we were you're going to make a decision about whether or not this was a good investment. Again, this is a cost alternative, not an investment alternative. So all that is for us right now is information. What is the capital recovery cost? Let's remember the capital recovery cost ignores all the periodic cash flows in this problem. All we're concerned about here is the initial investment, the $13,000, and the final market value, which is not the last cash flow. The final market value is an element of that last cash flow. The final market value is $3,000. So don't confuse the final market value with the final cash flow. They most often are different. The way to find the capital recovery cost, it's an annual cost, an annual amount, and this is very, very simple if you have your cash flows with the correct sign. So let me show you how we do this. This is P&T, the payment function, to give us a periodic payment or an A. The first argument is the rate. The rate is 12% for us. What's the next argument? The number of periods. There are 15 years in this investment. So I'll enter 15 right here in the second argument. The third argument is the present value. Well, the present value is the investment of negative $13,000. And the next argument is the future value, which is the market value at the end of the life of the project. Since that number, I haven't really entered that number, it's part of the last cash flow, I'm just going to type that number in as $3,000. Notice that I'm putting in exactly the same sign as the cash flows are. I'm closing that up, and there's the number, $1,828. Now, let me say something about that number. Notice the label on it is capital recovery cost. This is not a cash flow. So when we're not dealing with cash flows, the convention of positive and negative is something I don't stick to. We look at the label, and the label here is a capital recovery cost. So while it is $1,828 and it's a positive number, it's a cost, an equivalent cost. That's not a cash flow. This is not money out of our pocket, but it is representative of what this investment costs us each year over the 15 years of ownership for this particular asset, this power plant. So that's the capital recovery cost. That's how you calculate it. Okay, let's look at the next problem, which is problem 519 in the back of chapter 5 in your text. There's some words around this. I've put the table with the numbers in here, so we'll work primarily with that. Here are the relevant text. Assume that all cash flows occur at the end of each year, that the purchase and sale of this property, we're talking about rental property, are not relevant to the study. If VD's MAR is 6% per year, VD is investing in this, what is the future worth of VD's projected net income? So we want the future worth of VD's projected net income. Couple of things to point out. Looks like that the revenue is a gradient, a $100 positive gradient starting at $6,000 and ending at $7,000. Expenses also exhibit a gradient. In this case, the expenses are begin at $3,100 and the expenses increase by $200 each year for the 10 years. So I've added a column here of net cash flow because in order to solve this problem, we want to look at the net cash flow. That's what's really important. So I will create that by adding those two columns together. There's our net cash flow each year for the 10 years. And you can see that it exhibits some the gradient properties here. The first 2 years are the same because the change in the revenue starts out at 200 and then moves to 100. But other than that, it's a nice gradient amount. I'm going to use the NPV function because to find a future worth, since there's no net future value equivalent function, we will use the NPV function. I'm going to put it right here. Notice that the first cash flow begins at the end of year 1. So when I find the net present value, it actually will be at time 0 equal NPV, MAR of 6%, and the cash flows are going to be here. That's our net present value of all of these cash flows, $19,026. And the future worth, it doesn't specify in the problem at what point you'd like to find the future worth. We will find it at the end of year 10. So we're going to take this number and move it to the future, move it to year 10. Many ways to do that. As I've told you before, I like to use the formula. We will use the FV function today. Future value, the rate is the first argument, that's 6%. The number of periods we're moving ahead is 10. There is no payment amount, there's no annual uniform cash flow, just the present cash flow, which is right there. It's a negative 34,072. Notice that we don't want it to be negative. I did not put the negative sign in front of the future value like I should have. And there we go. So the future worth, the answer to problem 519, the future worth of VD's investments at 6% MAR is $34,072. And that's it. The many ways to solve these. Anytime we have non-uniform cash flows, the first thing that should jump to your head is using the net present value NPV function to solve those problems, to help solve those problems. Okay, there we have it. That's the initial part of chapter 5. We could have also found the annual worth of those projects, but we won't do that today. We'll do that in the next video. We'll look at perhaps an overall overarching problem. We'll look at all the different elements we can use to determine whether or not an investment is attractive. So I'll be posting that video up very soon, and we're getting the material now that we'll start reviewing when we get into class face-to-face on Wednesday. Hope you all have a good day.